Hi, good evening. Today, this is a part of the topic 52 discussions. This is for 9701 A level students of Cambridge International AS and A level. So let's have a look at our first question for October November 2016. This is just to give you a threshold values for where the A grade is and B and C. Now, the first question here. Remember, the first question in any A-level paper 52 referred as the planning question. The second one is considered as evaluation. So if you look at the first question here, it talks about a titration being used to figure out the concentration of the zinc ion using EDTA solution there. And they have given you a mathematical relationship between the zinc ions and the anion coming from EDTA, which is mentioned here in the question. As you see here, this happens to be 1:1. Remember, this paper is already solved by me, and I'm just giving an oral explanation as to why the answers were written the way they are. And as you see in this equation, there is also an H plus ion which is being released as a product. That means the solution will become acidic in time. So that's the reaction there. This is representing the EDTA there, and the relationship between that and the zinc ion is 1:1. Now, starting off with the first question, they said, explain why the pH would change during the titration if the buffer is not used. As you see here from this equation, there is H plus ion being released, which means you expect the solution to become slightly acidic over the period of time. And as the concentration of H plus increases, the pH value will actually decrease. And therefore, the role of buffer is to make sure that that doesn't happen. You know, buffer solutions are the ones which can withstand changes in pH when small amount of acids or alkali are added to it. So that's the reason why buffer is added in. But don't forget, don't expect buffer to be a magic solution. A buffer has a capacity which is called buffering capacity. There is a limit up to which how much acids or alkali you can add. That's why the definition of buffer clearly says a small amounts of acid and alkali, if it's added, it can resist the change in the pH. Now, the next question talks about we have the concentration, approximate concentration of zinc sulfate 0.1 is taken, but it's approximate concentration. So our job is to figure out the actual concentration. And they're giving you 20 grams of EDTA. MR of EDTA is already mentioned there, and the pH value mentioned at 10. The approximately concentration of zinc sulfate mentioned as 0.1 mole per dm cube. Indicator is also mentioned. Now, the first question here talks about what could be the three piece of volumetric apparatus you would use. Now, remember, it's a titration setup. So using your AS background, you know, for any typical titration, you need a burette whose volume is always 50 cm cube. You need a pipette whose volume is always 25 cm cube. And of course, you need a volumetric flask to prepare a standard solution. Now, there's a difference between volumetric flask and normal conical flask. Remember, the normal volumetric flask has a long, narrow neck, and it's a high precision glass there, which can very accurately measure up to 250 cm cube of whatever solution you are making. Conical flask and beakers don't give you accurate volume measurements, and they are just used for approximation. So these are the three things that you would want for your titration. Moving on to our next question. The next question talks about how would you calculate what would be the absolute accurate mass of EDTA that you need to prepare 250 cm cube of standard solution of 0.1 mole per dm cube. Now, they have given you the concentration of EDTA. They want you to make 0.1 mole per dm cube. Now, since we know we are using a 250 cm cube volumetric flask, which means we already know the volume that we need, we already know the concentration that we need, and of course we know the formula N equals to C times V. So we can punch in all the information there to get the value of the moles. Now remember, to keep the cm cube into dm cube, you need to divide it by 1000. So that's the reason why the 250 cm cube was divided by 1000 to change into dm cube. So once I got the moles of the EDTA, how to figure out the mass? Now remember the IGCSE formula, mass equals to moles into MR. So we already have the moles coming in from here, 0.025. We have the MR of EDTA given in the previous page, as I mentioned, and that's the reason why we get 9.305. So that's how this answer is calculated. And now the next question here talks about how will you prepare this standard solution? Now, this is an experimental procedure. The idea is to prepare 250 cm cube of the EDTA. I have written all the explanation here, but I will just explain it to you in a simpler format using some visual diagrams if you it might help you. So normally what we do, of course, we cannot add the solid directly into the volumetric flask. Remember, it kind of looks something like this, and it's very difficult for us to put the solid here and really mix it. So that's a 250 cm cube volumetric flask, and that's not exactly a good glass to make a solution. So what we normally do is we start with some kind of a beaker. Okay, so let's say I'm going to start with a 200 cm cube beaker. So that's a good way to start. And in the 200 cm cube beaker, remember the exact mass that we calculated was 9.305. So what I'm going to do is I'm going to add here solid 9.305 grams of the EDTA is carefully measured out and then put in this beaker. And in this beaker here, I'm going to add some distilled water. Now, I don't really have to add 250 cm cube distilled water. Remember, that's my target. And I need to make sure that the EDTA is properly dissolved. So ideally, what we recommend is to add about 100 cm cube of distilled water at the beginning and then take some kind of a glass rod there and then do some stirring to dissolve. And once you do that, then you need to transfer this using a funnel, and you could now put this directly into your volumetric flask. Now the thing is, while transferring, of course, that's your beaker. It's a rough diagram, pardon me. So just to give you an idea. And normally the stirrer that we used to mix up the solids there. So normally we use a stirrer here, and we just make sure that we carefully pour the liquid with the help of a stirrer, which then carefully comes down using the funnel into our volumetric flask. Now all the 100 cm cube approximately gets poured into the volumetric flask. Now remember, the total volume we need is 250 cm cube. Now what happens is when you do that, the beaker that you have used here, after you pour the liquid out, you would always find some drops of the EDTA solution will be stuck to the walls of the beaker. So we do a process called rinsing. And rinsing, basically what happens is we add more water into it, we add more distilled water into it, we just swirl the solution there, and we continue this. Okay, so that's, we repeatedly add a little bit of water and we continue adding water into the volumetric flask. The idea behind this is to make sure all the EDTA solid has been transferred out from this beaker. You don't want any solid particles to be left behind, and you don't want any liquid drops which could have some EDTA still in it to be left behind. Remember all the time that the total volume should be approximately 200 cm cube. You don't want to hit the 250 mark, don't forget. So maybe rinsing could be done with another 50 cm cube and 50 cm cube. Two times you can do rinsing. So the total amount of water now you've added is about 200 cm cube. And then the final remaining 50 cm cube of water is carefully added using wash bottle, and we make sure that we remember it's a colorless liquid. For colorless liquid, the lower meniscus of the liquid must touch this is the lower meniscus. I'm just giving an approximation there. The lower meniscus of the liquid must touch the line. That ensures the correct amount of water has been added. And then don't forget to put a cap on it. And after putting the cap on it, we just mix or swirl the solution to make it homogeneous. And that's what is actually what is mentioned in my comments here. Okay, so I hope that gave you the explanation in this page, just to give an idea how actually it will be done in your AS labs. And once we let's have a look at our next question there. After you perform a rough titration, remember the rough titration is done very quickly, that just to give you and get an idea where approximately the endpoint would be. Then this question says, after you perform a rough titration, which is never considered as an accurate titer, how would you ensure that the next titration is accurate? Now remember, the rough titer already gives you an approximate endpoint. So you know, for example, if the endpoint was 26.1, remember you don't say 26.1, you have to say 26.10 or 26.1, 10 or 15. Remember, the second digit after decimal during titration has to be 0 or 5. Now, once we have approximate rough reading, when you come close to that reading, when you do the titration the second time and the third time, we have to go drop by drop when we come close to that point. That is to ensure that whatever reading we get is more accurate. So that's the reason why I've written here, we add dropwise when we come near to the endpoint. Endpoint is where the indicator changes color, the titration gets over. And the next question talks about how would you ensure that the titration result is reliable? Well, the only way to do that is to repeat titration 2-3 times and to get the consistent reading or concurrent reading, which actually means readings which are approximately either same or 0.1 close to each other. Now, let's have a look at the C part here. There's an equation given, and this equation now deals with the calcium ion, magnesium ion, and it talks about calcium ion and magnesium ion being present in hard water. Hard water basically which doesn't form lather with soap. Not very good for us really. It kind of doesn't help us in anything. We don't use hard water. We need to convert hard water into soft water. And basically water becomes hard if it contains calcium ions and magnesium ions. And this is what's coming from the EDTA, remember? So if you look at the ratio, the mole ratio here, I have 1 mole of calcium, 1 mole of magnesium, and 2 moles of the EDTA ion which is coming, which kind of means that the relationship between calcium and EDTA is 1:1, and relationship between magnesium and EDTA is 1:1. So I hope you understood that. So basically each of this positive metal ion has 1:1 relationship with the EDTA. Okay, and now we need to read this too very, very carefully. I need you to read this too carefully to understand what's the difference between the first titration and the second titration. Now, 25 cm cube of hard water is taken. That's the one which is going in your conical flask during titration in both the cases. So 25 cm cube, that's a standard volume of whatever we take and goes into the volumetric, into conical flask. Now, the EDTA is coming from the burette. Now, the concentration of EDTA is 0.01, which is mentioned. That's the one which comes from the burette. The indicator is added to the 25 cm cube of the hard water, which is taken in the conical flask, measured by pipette, which is 25 cm cube. Now, if you look at the difference between the two titrations, in the second titration, the examiner says second titration is done after adding sodium hydroxide into the sample of hard water, which removes all the magnesium ions out as a precipitate, which means in your second titration, what's left in the hard water after the magnesium ions has been kicked out is only the calcium ion. So only calcium ion and EDTA are interacting in the second titration. However, in the first titration, nothing of that was done. The sample of hard water was taken, and don't forget, hard water contains calcium ion and the magnesium ion, and that's the one which was interacting with the EDTA solution. So that's the difference between the first titration and the second titration. Remember, in the second titration, the magnesium ions were removed out, so only the calcium ion is interacting with the EDTA. So once we are okay there, always remember, whenever they give you information about some chemicals, there probably would be a question coming in for safety. Corrosive, definitely think of the gloves. If something is irritant to eye, think of the fume cupboard. Usually, these are the good things to good. Normally, you will always have questions, as you see here, of what would be the risk issues and how would you reduce the risk issues. So because NaOH is corrosive, so best way is to wear gloves. or alcohol is flammable, so you don't want to put that alcohol near any flames which could be burning in the chem lab, particularly Bunsen burners. You don't want to do that. And something which is irritant to eye, best way to tackle that is to do that experiment in a fume cover. Now, have a look at this calculation. This is probably where most of the students need help. Remember, once again, the second titration only calcium ion was interacting with EDTA, but in the first titration, calcium ion and magnesium ion both were interacting. That's the reason why when I solved this paper, I looked at the second titer first. And in my second titer, I know my EDTA is coming from the burette. So the 16.60 cm cube is the volume of the EDTA which came from the burette. And don't forget, they already gave you the concentration of EDTA as 0.01. So I have the concentration and I have the volume. And once again, don't forget the cm cube must be divided by 1000 to change to dm cube. So that's how we got the moles of the EDTA. Now, as I mentioned in the beginning, the relationship between the calcium ion and the EDTA is 1:1. So whatever is the moles of the EDTA is equal to the moles of calcium ion. So that's how I got the moles of calcium ion also as 0.000166. Now, remember the amount of hard water taken was 25 cm cube in the second titration. And the calcium ion is in that 25 cm cube, which means that's the volume of the calcium ion. The volume of the hard water is the volume of calcium ion. And that's why we put that in the formula. We need to find concentration of calcium ion. So we know C equals to N by V. So the moles of calcium ion is already calculated here. The volume of the calcium ion happens to be 25 cm cube, which again divided by 1000 to convert into dm cube finally gives us the correct answer here. That's the concentration of the calcium ion. That's how this was calculated. Now remember, in the first titration, the calcium ion and the magnesium ion both were present. Now that's important. Calcium ion and magnesium ion both were present. Now which means this volume which was used of EDTA in the first titration, 22.70, we know from the second titration that this is the amount of EDTA which is required for calcium. This is needed for calcium. Now in the first titration, 22.70 is needed for calcium plus magnesium. And I know from the second titration that for calcium I need 16.60. So I hope you understand now where I'm going with this. So what I do is from 22.7, if I subtract 16.6, if I subtract, and the reason I'm subtracting, because this is good for calcium. This is good for calcium plus magnesium. So when I subtract that, the amount of volume that I get, 6.1, is exclusively used for magnesium ion. So 6.1 cm cube of EDTA 0.01 concentration was exclusively used to get rid of all the magnesium ions in my first titration. So I do the same math again. So I know the concentration of EDTA is 0.01. The volume of the EDTA is 6.1 after that subtraction. And that helps me to figure out the moles of EDTA. And don't forget that the relationship between the EDTA and the EDTA is still 1:1. So the EDTA and ratio calcium ion, magnesium ion is 1:1. Don't forget in the previous page, the ratio was clearly mentioned, the equation. So whatever is the moles of EDTA is the moles of magnesium ion. And that's how I can now directly use that in my concentration. I know C equals to N by V. So the moles that I'm getting, this moles is of EDTA, which also happens to be now the moles of magnesium ion because it's 1:1. So I just put that value here. And don't forget the volume of hard water used in the first titration is also 25 cm cube, which happens to be the volume of magnesium 2 plus ions also. And that's the reason why that was the volume used. And don't forget, we divide by 1000 to change into dm cube, and that's how we got this answer. So that explains the calculation for this question. I hope the whole explanation makes it easy for you to understand. Feel free to write comments and let me know. if you have any questions or doubts. Thank you very much for watching.